Hello, everybody. Welcome to the Henstitute. This is Mr. Hennon. This is the last part of Chapter 14. It's amazing. Chapter 14 is actually pretty small. We talked about moles, we talked about the gas laws and the ideal gas law, and now we're going to finish up with kinetic theory. So all things that kind of relate to chemistry, but really more of a physical chemistry kind of idea. So in this particular concept, one of the things with kinetic theory that we have to do is kind of make some assumptions. So these are all of our little assumptions that we're going to make. One, the number of molecules is very large, but their separation is large compared to their molecular size. So we're basically saying that they're so spread out that they don't really interact with each other. So molecules are going to move randomly. So this is one of them. Molecules are going to move randomly with a distribution in speeds, which does not change. So they're moving all over the place. You're going to see that in the picture in a moment. The molecules undergo elastic collisions. It's going to be very important. So when they hit the walls or they hit other molecules, they're going to not lose any kinetic energy. That's very important. That's what an elastic collision means. And finally, we're going to assume that these molecules obey Newton's laws of motion. So these are assumptions that we make. At the molecular level, it's not the perfect situation if you want to be really picky, but it's going to lead to good macroscopic relationships, and we're going to be fine. So this is our idea. Let's imagine we have this box over here. So this is our box, and it's full of some kind of gas. So these are gas particles. And the idea is they are moving around, so they're going to come along, they're going to collide with the sides, but they're moving with different speeds. So each collision is going to change that particle's speed. We have them moving with all kinds of different speeds, and the idea is, how do I go about trying to find its kinetic energy? Or you've probably all heard the idea that temperature is a measure of the average kinetic energy. How do we get that statement? Where does that kind of come from? So that's what we're leading into. The first thing we find is, since they're moving at all different speeds, we can come up with a distribution of those molecular speeds. And it all depends on the temperature of it. So this particular one is, we're assuming this gas is at 300 Kelvin, and what it does is it gives kind of the percentage of molecules that have a particular speed. So if you notice that we get a distribution that almost looks like it's going to be a bell curve, but this end of it always stretches out a little bit more. So you'll notice that this side of it is a little more stretched out than that side of it. And then the higher the temperature, you'll actually get it to flatten out. So it's still a curve, but also you're going to get it to trail off a little more over here. So I can move myself up here. And so this trail over here is actually coming off more than that side. But we get to what we call the most probable speed, which is really the top of these particular curves. That's the most probable speed, and higher temperature, higher speed, as you would kind of imagine, just kind of an idea of motion. Well, James Clerk Maxwell actually came up with a speed distribution and kind of talked about all the different parts of it. And so this is another one of those little curves that I just kind of showed here. And so we have our most probable speed, which is the top of it. But this is actually not the one that's the most important. What we'd really like is the speed that's right in the middle. So the speed that's right in the middle of this particular distribution is not the most probable speed. The most probable speed is just going to be the one you have the most values with. And then it's not actually even equal to the average speed. The average speed falls a little bit there. This is going to be what we refer to as the root mean square speed. So it's kind of a weird one. We're actually taking the square root of the average squared, which sounds like that should just give you back the average, but it's slightly shifted from it. But it's the best value that we have, and it's really the middle. It's the median value of these speeds, and that's what we actually want to do. So we're not picking the mode. This is the mode over here. This is the one we have the most of. We're not picking the mean. We're actually going to pick the median speed. So how do we go about it? We're really going to start off with Newton's second law. Look at this, Newton's second law, which is awesome because this is what I'm actually talking about in Physics 1 right now. So F equals ma. So when I think of a particle coming in, I'm just going to do a simple example. Let's have a particle moving this way and then bounce off the wall, and then it's going to move in the opposite direction. So I have those different speeds there. So to find that force that it's going to apply to the wall or the wall applies to it, it's going to be m times a. But the change in velocity can be kind of lumped together with this. And this is another way to write F equals ma. We write it as the net force actually equals the rate of change in momentum. So m times v is the momentum. So our average force is final momentum minus initial momentum over the time between the collisions. So momentum is just mass times velocity. So afterwards, we have the particle moving in the negative direction. Originally, it's moving in the positive direction. So you have a negative mv minus mv. That's actually going to give you two of them. So on the top, we'd have minus 2 of these mvs. And then for time, the idea of this is we imagine that this particle is going from one wall, hitting this one, and then bouncing back to that wall. So it's moving back and forth between these two things. Whoops, let's go back for a second. And the idea is the distance from wall to wall would be L. So if you're going to one wall and then bouncing back, you're going 2L for your distance, and you're moving with a certain speed. So if I think of speed being equal to distance over time, if I flip these, we can find our time by taking 2 times that L over our speed. So that's what we put in down here. Guess what? That 2 and that 2 are going to cancel. This divided by v is going to bring it up here, and so we end up with this idea, minus mv squared over L, where L is the size of your box, so it's the width here. That's for a single molecule. So this is the force that a single molecule would apply to a wall, or the wall applies back on it, Newton's third law. But if I have n number of molecules in this particular setup, let's see if I can grab myself again. Oh well. Then all we're going to do is we're going to multiply, you would think, just by n. But if you notice, you'll end up with this n over 3 situation, this little 1/3 situation. Where that's coming from is we have 3 different directions this can go. So a particle can go side to side, it can go up and down, or it can go forward and backwards. Since we have 3 different dimensions, we have to think of those particles as moving in each one of those, and that's where the 1/3 comes from. And then this is where we're going to suddenly switch this from just a v of a single molecule into the root mean square speed. So you can write it like that, but we typically write v RMS. That's the way we're going to eventually write it. So this gives us the force. And then we're just going to take it to the next step and talk about pressure. So pressure is force divided by area. Well, the area would be the area of this wall, because we're hitting this wall with a certain force. So the area of that wall is just length times length, because it's just a square. So we get F over L squared. We replace our F right here, and then we end up with an L cubed. Well, L cubed is just going to be the volume of this entire thing. So we're slowly kind of going through equations. This is not something you'll have to do every time. I want to lead you into that final equation. So the pressure that this is going to apply on any of the walls in here, the pressure of these gases, molecules, is going to be n over 3 times mv squared over v, big V. This is the volume. I can take this big V and bring it over the other side. So now I write it as pressure times volume. Hey, PV, I'm familiar with that. In the ideal gas law, that's equal to nRT. So this could be the number of moles times the ideal gas law times temperature. Or since we've got this in terms of actual number of particles, it might be better to use PIV-NICT, where we've got the number of particles, the K is the other gas law constant, and then temperature. So I can replace that in here for PV, and we end up with a nice little relationship here that we've got our 1/3 mv squared, and that's this part right there. And then we can kind of pull some things out. One of the things we like to pull out is we pull out a 2 here and a 1/2 there. And then we can write this as 1/2 mv squared. And notice that we kind of switched over. This is just the book, kind of doing this into the RMS. And this is kinetic energy. So I can think of this as the average kinetic energy. It's equal to 1/2 m times the RMS speed. And that is going to equal my PV, but it's actually equal to a 3/2 times that, because here's what I ended up doing to kind of show that. I've got this 2/3 n there, and so when I can cancel out the n's on this, and then I multiply by 3/2. So here's what I had is this little nkt was equal to 2/3 n, and then this is that average kinetic energy coming from that right there. And then these ends cancel out. I bring the 3/2 and we've got this. And this gives us a nice little equation that can actually relate the average kinetic energy with temperature. So this is why we talk about the temperature is the measure of the average kinetic energy. They're related to each other because K is a constant, 3/2 is a constant. So let's try a little sample problem. Here's our sample problem. Air we know is mostly nitrogen and oxygen, and I've got the molecular masses of both of them. Let's assume that each behaves as an ideal gas. It's kind of a common thing that we do. We're going to try to determine the average, the root mean square speed, so the speed of these nitrogen and oxygen molecules in air temperature that's at 293 Kelvin. 293 Kelvin is 20 degrees Celsius. So you're talking about somewhere around 70 degrees Fahrenheit, somewhere in there. So if I take this concept and I kind of rearrange it, this is probably the way we'll write this equation most often. This is what I would probably put on my equation sheet, or you could put this on your equation sheet, either one. But it's a great way of finding the RMS speed. We often want to know the RMS speed. So let's look at the oxygen, for example. I know the temperature, I've got that, so there's my T, so that's not a problem. K, if you remember, this little k was the ideal gas law. This was the 1.38 times 10 to the negative 23, and it was in joules per Kelvin. So these are a couple of constants that we want to make sure are on our equation sheet as well. We'll go over that later. But I can put that in. For the mass, I actually need the mass of the oxygen molecule. Now it's a diatomic molecule, so it's O2. So when they give us this 32, that's already given to us. So that's 32 atomic mass units. But I have a nice little conversion, 1.66 times 10 to the negative 27th kilograms in 1 atomic mass unit. So that's one way to think of it. Here's another way to kind of think of it. We know there are 32 grams in 1 mole. That's another way to think of this. And we know that 1 mole is 6.02 times 10 to the 23rd particles. So we could actually do a little conversion and get grams per molecule. And so this would give us the grams for the number of grams for one of those items. And that's basically where this number comes from. So either one of them will change it into our kilograms. So I'm going to do that real quick. 32 times the 1.66 times 10 to the negative 27. So I get 5.312. So our mass of oxygen here is going to be 5.312 times 10 to the negative 26 kilograms. So we got to be able to change this into kilograms. We're going to use that conversion factor a lot. I can plug that in here, plug in my temperature. Let's see what kind of value I get. The square root of 3 times my 1.38 times 10 to the negative 23. And then I'm going to multiply by the temperature, 293. And then I'm going to divide it by the mass, this 5.312 times 10 to the negative 26. Chunk that out, and I get about 478 meters per second. So the oxygen molecules in the air, when it's about 70 degrees Fahrenheit, are moving at about 500 meters per second, a little less than 478 meters per second. Pretty amazing. You can also do this with nitrogen here. Nitrogen being slightly lighter would actually be moving slightly faster. So if you notice, it ends up with a speed that's a little bit larger than that. So that kind of relates that concept as well. Last but not least, we often talk about the internal energy of a gas, and we're dealing with monatomic gases right now. That's the easiest way to kind of think of them. And the average kinetic energy, we can think of the entire internal energy of that gas. We use the letter U to represent that, is just going to be equal to that average kinetic energy of one molecule times how many molecules you have. So you're just going to multiply by N. This is kind of neat. If you write that, then U is equal to N 3 halves KT. But wait a second, NKT, isn't that the same thing as PV? So you could actually write this as 3 halves pressure times volume, or 3 halves nRT. So you got NICT, NERT, or PIV. All of those are going to kind of fit. So this is kind of my lesson on kinetic theory of gases. I'm going to throw some problems at you, see what we can kind of figure out, and that pretty much sums up chapter 14. And then we'll be ready to finish out thermodynamics and talk about those laws. Hope you enjoyed this edition of the Henstitute.